Hey, Algebra 2, Lesson 4, Properties of Exponents and Radicals. We've done a lot of the basics for radicals and exponents. Now we're going to apply it a little bit as things get just a tad bit harder. First, some review. Okay, try these ones on your own. Write each exponential expression as a radical expression, then use the definition and properties of radicals to write the resulting expression as an integer. I'll do the first one for you, and then I'm going to push pause and have you try to do the ones on your own. Okay, so here I can change 7 to the 1/2 to the square root of 7 times the square root of 7, and we know that the square root of a number times the square root of the same number gives us the number. But we can say that is going to be the square root of 49, which gives us 7, right? Okay, I'm going to push pause, and you can try these next ones. All right, check those answers out and see if you got the same thing. You may have tried the problems a little differently than me, and that's all right, as long as we get the same results. So, how could we write the square root of 7 times the square root of 7 equals 7 with rational exponents? Really, this is the same as 7 to the 1/2 times 7 to the 1/2. Which we learned a rule that said that is 7 to the 1/2 plus 1/2, which equals 7 to the first power, which equals 7. The same with the cubed roots. Okay, we had all of these. It's really the same as 3 to the 1/3 plus 1/3 plus 1/3, which is 3/3, which is 1. So that equals 3. Okay, our rule is b to the m times b to the n equals b to the m plus n. You need the same base. Okay, this has to be the same as this is, and that is, right? We have the same 7s. And then you can add the exponents. Sort of fun. But that's our rule. Okay, the next set of examples, the instructions say write each expression in the form of b to the m over n for positive real numbers b and integers m and n with n greater than 0, right? That's the denominator. It can't be equal to 0, by applying the properties of radicals and the definition of the nth root. So by the definition of the nth root, I'm going to go ahead and change these. I've got the 4th root of b times, not plus, times the 4th root of b. That gives me the 4th root of b times b, all underneath the radical, which gives me the 4th root of b squared, which I change into m over n, that's 2/4. Or 1/2, right? If I go straight to our addition, it's really 1/4 plus 1/4 equals b to the 2/4, which is b to the 1/2. Okay? How about b to the 1/3 times b to the 4/3? If I change them all into radicals, I could say that's the 3rd root of b times the 3rd root of b to the 4th power, which gives me the 3rd root b times b to the 4th power. You have to remember your power properties, your exponent properties. That would be b to the 5th power, because I add 1 and 4, which is b to the 5/3. Okay? Or I can go straight 1/3 plus 4/3 equals 5/3. Cool? Okay, let's try this one. Notice I don't have the same denominator. So I really need equivalent fractions first. So if I have b, my common denominator would be 20. So 5 goes into 24 times, 4 times 1 is 4, times b to the 4 goes into 25 times, 5 times 3 is 15. So we have 4 over 20 and 15 over 20. So if I went radical route, 20th root, what? B to the 4th times 20th root, b to the 15th, 20th root, b to the 4 times b to the 15th, 20th, add those together, b to the 19 over 20. Okay? Or go directly here. Actually, I'm going to go directly from here since I don't want to do that work again. B to the 4, 20 plus 15, 20 gives me 19, 20. Cool. Okay. So really what we've learned here is a rule, b to the m over n times b to the p over q. Oh goodness. P over q, that's a p, equals b to the m over n plus p over q, where you may need to get common denominators, right? But that's not a problem. You guys are good at fractions. Okay, other fun rules you may want to jot down. I'm just going to list them out. B to the m over n is the same as nth root of b to the m, is the same as nth root b to the m. That m can be underneath a radical or outside of it. It doesn't matter. B to the 1 over n raised to the nth power is the same as bn over n, b to the 1, b, right? You guys are going, well, duh. I can flip that. B to the n raised to the 1/n. Okay, remember you multiply your powers when you have a power raised to a power. N over n. Okay, little bit of a review, right? How about a b to the m over n is the same as a to the m over n times b to the m over n. I need a new sheet, a new slide. Continuing on, what about b to the m over n raised to the p over q? That would be b to the mp over nq, because you multiply the fractions, right? I'm racking my brain for many different examples. How about if they went negative? That's the same as 1 over b to the positive. Not sure I can think of much more. I think that's it. All right, try these practice exercises. I'll do the first one. We're skipping that middle step where we had to write everything in radical form and then get it back. Here we just are going to do b to the 2/3 plus 1/2. I need a common denominator. So it looks like 6. 3 goes into 6 twice. 2 times 2 is 4. Plus 2 goes into 6 3 times. 3 times 1 is 3. Gives me b to the 7/6 as an answer. Okay. Here I'm going to multiply. So b to the negative 1/5 times 2/3. Let's change how I write that. Power to a power, we multiply the exponents. So I have b to the negative 2 over 8, which I would want that as a, well, oh, 2 over 8. That's hilarious. I caught it. I caught my mistake. 15. And we're not going to move it to the denominator. It's all right. Try these two on your own. Okay, I'm going to push pause. All right, with these two examples, you can see what I did. Added my exponents. I needed common denominators, so I got 64 to the 11 over 6, which I changed into a radical. 6th root of 64 raised to the 11th. I don't like that underneath a radical, though. I'm not going to actually calculate 64 raised to the 11th power. It would be a huge number. So I moved 11th power to the outside of the radical. So I have the 6th root of 64, which when I was doing the homework the other day, I now know that the 6th root of 64 is 2, but you guys could figure that out using your awesome calculators or just testing a really small number. So 2 to the 11th power, I got my calculator out and did 2 to the 11th power and got 2048. Cool. So I know I've told you guys to try these without your calculator as much as possible, but really 2 to the 11th power, go ahead and try it. Okay, here I have something raised to a power, so I need to multiply it to the numerator and the denominator. 3 halves times 3 is 9 halves. 3 halves times 2 is 6 halves, which simplifies to 4 to the 3rd power. Here I changed it to radical square root of 9 raised to the 9th power. I went ahead and put this on the outside of the radical because I know there's a square root of 9, which gives me 3, and I really don't want to raise 9 to the 9th power because it would be a very big number. So 3 to the 9th power, calculator, big number, and 4 to the 3rd power, I'm starting to memorize, 64. It doesn't give you a whole number for the division, so you can just keep it in a big fraction, right? All right, rewrite the radical expression so that no perfect square factors remain inside the radical. So we need to simplify this. How I simplify them is I break them up first. So 48, x to the 5th, y to the 4th, square root of y to the 4th. That looks awesome. There we go. And square root of x squared. 48 breaks into 16 times 3. So the 16 comes out of the radical, 4 square roots of 3. Here, this breaks up into x to the 4th times x. X to the 4th comes out of the radical into x squared. This one comes straight y squared. And that one comes straight out as an x. Let's gather our, I would call them like terms, get everything that is out of the radical together, and then gather the things that are under the radical together. Cool? Okay, use the definition of rational exponents and properties of exponents to rewrite each expression with a rational exponent containing as few fractions as possible. Then evaluate each resulting expression for x equals 50, y equals 12, and z equals 3. So let's go ahead and simplify this. Now, the curriculum wants us to really break all of these into rational exponents first. And you can. That's great. Like for the first one, you have 8 to the 1/2. That doesn't help me solve that much because it's a number. So I break it into its factors and look for perfect squares. 4 is a perfect square, so I know I can take that out of the radical, make it a 2. 2 squared is a 2. For this next one, x squared is a perfect square. X is not. X squared comes out of the radical and becomes an x. X stays under there. Y squared is a perfect square. It becomes a y. And then I collect like terms. 2xy square root of 2x. Okay, now we're going to replace it with numbers. 2 times 50 times 12 times the square root of 2 times 50. 2 times 50 is 100 times 12 is 1200. Square root of 100. 100 is a perfect square because it breaks into 10 times 10. So this gives me 12,000 as an answer. Cool. Okay, cubed roots, a little harder. I'm still going to break it into its pieces and parts. Cube root of 54, cubed root of y to the 7th, and cubed root of 7 squared. This one I'm actually, 54, it's not 3, it's not 4. I think 54 gives me a 27 and a 2. 27 is a third root, so I've got three cubed roots of 2. Okay, this one I'm actually going to do a fraction. So y to the 7 over 3, which is y to the, let's see, 3 goes into 7 twice, 2 1/3, and then y to the 2/3. That fraction is a proper fraction, so I can't do anything with it. Oh, that's a z though. So here, I know I'm good with that one, right? So if I collect all my pieces and my parts, I'm going to have 3 outside the radical, y squared outside the radical, and that's it. So 3y squared, and then what's left underneath there, I have the cubed root of 2 and a y and a z squared. It's just a y because that is just the first power. So that'd be 1y third root left over, 2 of the z's to the third roots left over, right? So that gives me my answer. Let's replace it with the numbers. I have 3 times y squared times the third root of 2 times y times z squared. So 3 times 12 squared is 3 times 144. Times the cubed root of 2 times 12 times 3 squared is 216. Which gives us 3 times 144 times 6. 2592. That's a 216. There we go. Okay? So we're going to find you guys will all find your easiest method for doing this. I'm going to show you one more way. I'm just going to do that one more way. Just bear with me. Because some of you will struggle with this and some of you will be like, what? This is easy. All right. So I'm going to change all of these to fractions. 54, I'm going to go ahead and say, hold on, 2 times 27, because I know 27's a cube root. So 27 to the third power times 2 to the third power times y to the 7 over 3, right? Times z to the 2 over 3. Okay, this one simplifies to 3. This one gives me, like I said before, y squared times y to the 1/3. Because 3/7 is an improper fraction. If I change it to a mixed fraction, I would have 2 and, because that's 6, yep, and 1/3. So that's y to the second power, y to the 1/3 power. I'm just going to move that down a little bit. So 3 times y squared times, I have a 2 left over, a y left over, and a z squared left over. All of these are to the third power. Okay, that one came over here. I have these left over and that one left over. So that's like a 2 to the third power, a y to the third power, and a z to the 2/3 power. So those are all simplest fractions. Okay, there are no mixed numbers, there are no improper fractions, they're all the simplest fraction, which is why this can be simplified to that. It's like I factored the 1/3 out, right? So another way to look at it, Here is just a summary of a lot of the things I wrote quite a few slides ago where I just sort of emptied my head of all the rules. I assume you wrote them down last time. They'll be at the top of your problem set, but it's things that'll make your life easier as you go through the problem set. That's all for today. Good job.